Hello everyone, this is Vipul Purohit and I welcome you all to my YouTube channel. Now my dear friends, as you can see, the title of this particular video is about Carnot Cycle. So we are going to learn over here what is Carnot Cycle all about and what is going to be its efficiency. This is going to be the content of today's session. So my dear friends, giving you a brief history, and that is way back in the year 1824, a French engineer named Nicolas Carnot was very much interested in understanding the steam engine being converted into the heat coming out of the steam engine being converted into work. So he was the first person, my dear friends, to derive a relationship between the efficiency of the heat engine or the steam engine with respect to the temperature which is involved in the process. Alright, so once again I repeat, he was the first one to derive a relationship between the efficiency of a heat engine or a steam engine with respect to what the temperature involved in the process. And for this particular purpose, he proposed a hypothetical steam engine which consists of the following parts. So the hypothetical steam engine consists of the first part, and that is a cylinder which is fitted with weightless and a frictionless piston. Second, point number 2 is 1 mole of gas being enclosed in the cylinder. Number 3, we talk about is hot reservoir. Now when you talk about a hot reservoir, is basically we talk about the source of heat. Next, the fourth one we talk about is a cold reservoir, and that's going to be the sink of the heat. I hope you understand the difference now between source and sink. Okay, source, that is from where the heat is going to be generated, and sink means where the heat is going to be absorbed. And then finally, we have an insulator. Okay, finally what we have is an insulator. So this is, my dear friends, the introduction part of this Carnot cycle. Just a brief recap once again of this, and that is in the year 1824, a French engineer named Nicolas Carnot was very much interested in understanding the conversion of the heat coming out of the steam engine into work. So then he was the first one to derive a relationship between the efficiency of heat engine to the temperature which is involved in the process. Now for this particular purpose, he designed a hypothetical steam engine which is consisting of the following parts. The first one is a cylinder which is fitted with a weightless and a frictionless piston. Next is we have 1 mole of gas, then a hot and a cold reservoir, and finally is the insulator. Now my dear friends, the entire process takes place in 4 different steps. Now these 4 different steps I'll try to explain you with the help of a diagram. So let us have a diagram first of all in front of you, and then I'll explain you each and every steps. So we have a curve that is with respect to the pressure as well as volume. We're going to consider over here, as I said, 4 steps. So we go for A to B, Next thing is we go from B to C, then we go from C to D, and then the system returns to its original state, and that is A. So you can see this, it's like a cyclic process. You know what is a cyclic process is? Okay? The initial state and the final state is same. We start from A and we end with what? A. Now the 4 steps which I was talking about, the first step, that is A to B, we call it as isothermal expansion. Okay, we call it as what? Isothermal expansion. The second step, we call it as adiabatic expansion. The third step, we call it as isothermal contraction. And the fourth step is adiabatic contraction. So we go from A to B, then we go from B to C, then we go from C to D, and finally the system returns to its original state, and that is D to A. Okay, so this is the diagram. 4 steps are there. I'll explain you one step at a time and see whether you understand that. I'll go as slow as possible. So we begin with step number 1. Now when I talk about step number 1, it is known as isothermal expansion. Now when I talk about isothermal expansion, it's all about 1 mole of a gas. Now the gas is going to be placed in a hot reservoir, and therefore the temperature that we are going to consider is, here I will be writing down as V1, P1 and T2. So it's a higher temperature. Here it will be V2, P2 and T2. Here it will be V3, P3 and T1. And here we have V3, P3, T1. I'll explain you all these. So initially we start with a hot reservoir, so the temperature is high, so that is going to be T2. Now what happens is, I allow this gas to expand isothermally and reversibly from a volume V1 to V2. So there is going to be a change in the volume. Obviously with that there will be a change in the pressure as well. Now due to this expansion, the cooling of gas takes place. Due to this expansion, what happens? Cooling of gas takes place. But if you can see, the condition is what? Isothermal. So if I want to maintain the isothermal conditions, then a quantity of heat, and I call it as Q2, is taken from the source, so that the system comes back to the original temperature. Alright? So once again I repeat, initially the gas is being placed in a hot reservoir. Next, it is allowed to expand isothermally and reversibly from a volume of say V1 to V2. Now due to the expansion taking place in the isothermal conditions, there is going to be cooling of the gas. Now because of the cooling of the gas, there will be a change in the temperature. Now to maintain the isothermal conditions, so what has to be done is, the temperature has to be raised, and how it can be raised is by absorbing Q2 amount of heat from the source. Now my dear friends, as far as the mathematical expression is concerned of the first law of thermodynamics, I'll just write down in short the first law of thermodynamics. So we have over here, and that is delta E is equal to Q plus W. Okay, it is delta E is equal to what? Q plus W. Now what happens is, when you talk about delta E is equal to Q plus W, now we try to make this equation in line to the isothermal expansion of the first step of Carnot cycle. So, because it's the first step, so I write it down as delta E1. Now, the amount of heat which is absorbed over here, I call it as Q2 because it is absorbed. So, it is positive. Next thing is the work is done by the system and therefore I introduce a negative sign. You know the sign conventions very well. The work done by the system is negative. On the system is going to be positive. So, I will write it down as minus of W1 because this is the first step. So we have delta E1 is equal to Q2 minus W1. So this is what we can talk about the change in the internal energy for the first step, which is being given as isothermal expansion of gas. So I hope you have understood this first step very well. Alright, my dear friends, now we proceed to the next part, and that is about step number is 2, and that step number 2, my dear friends, is adiabatic expansion. So what we are going to do now is the gas is going to be placed in an insulator. So as a result of which there is no exchange of heat going to take place, and I am going to allow it to expand adiabatically and reversibly from a volume of V2 to V3. Now my dear friends, as a result of adiabatic expansion, please remember that there is a decrease in temperature. So that's the reason what we have written is T2 to T1. T1 is a lower temperature, T2 is a higher temperature. So if you can recollect, when I started with the first state, that is A, we said that the gas is being kept in a hot reservoir. So the temperature is going to be high. It's isothermal, so the temperature remains constant. Now, as we go for an adiabatic expansion, there's going to be a decrease in temperature, and that is we go from T2 to T1. Okay, so it results in a decrease in temperature from T2 to T1. Now, when we go for the change in the internal energy, I write down this sign, this is the second step, so it is delta E2 is equal to Q plus W. This is what according to the first law of thermodynamics is all about. Now, because it is adiabatic, there is no exchange of heat taking place, and therefore we say that Q is equal to what? 0. So what we now have is delta E2 is equal to, this is going to be 0, minus of W2. Okay, the work is done by the system. So as a result of it, it's going to be having a negative sign. So we have delta E2 is equal to minus of W2, and this is, my dear friends, the second expression of step number 2, and that is adiabatic expansion. I hope you have understood up to this very well. Alright, we move now into the step number 3. When we talk about step number 3, as you can see, that we are now heading towards the contraction process, and that is, we call it as isothermal contraction. Now when I talk about isothermal contraction, we are going to say that here the gas is compressed isothermally and reversibly. Now here, my dear friends, please be very clear, we are now going into the cold reservoir. Okay, initially it was a hot reservoir from A to B, from B to C we talk about insulator, and now when we go into the step 3, that is C to D, we are going into a cold reservoir. Okay, now as a result of this isothermal reversible compression taking place, what is going to happen is the gas is going to be heated up. Okay, the gas is what? Heated up. Here the gas was cooled as a result of isothermal expansion. The opposite process takes place. It is isothermal contraction, so gas is heated up. Now I want to maintain the isothermal condition, and because of that, the Q1 amount or the Q1 quantity of heat is being released. Okay, and when it is being released, so that means it will go towards the sink. So previously we had a source when I talk about a hot reservoir. Now when I refer to a cold reservoir, it goes to the sink where that heat release will be absorbed. And as a result of which now, my dear friends, if you go for the first law of thermodynamics, which says that delta E is equal to Q plus W. So here we have delta E3 because it is step number 3. We have now minus of Q1. Why minus of Q1? Because the heat is released by the system. So exothermic, so it is negative. The work is done by the system. So we say here minus of W3. So this is, my dear friends, the expression for the third step. That is delta E3 is equal to minus of Q1 minus of W3, and this particular step, my dear friends, is known as isothermal contraction. I hope you have understood up to this very well. Yes, my dear friends, now we move on to the last step, and that is going to be step number 4. Now here in this case, you must be knowing it very well. You can read here from this diagram. Step number 4 is all about adiabatic contraction. Now here in this case, when you talk about an adiabatic contraction, the gas is being subjected to an insulator. Now as a result of the adiabatic contraction, there will be increase in the temperature. It's the opposite process. If you can recollect, I told you during adiabatic expansion, there is going to be a decrease in the temperature. Now here in the adiabatic contraction, there is going to be an increase in temperature. So it goes from T1 to T2. Next is we talk about the compression of a gas taking place, and the compression of the gas which is taking place, the condition is going to be adiabatic and reversible. Okay, adiabatic and reversibly compression of the gas taking place from a volume of V4 to V1, right, from a volume of V4 to V1. Now here in this case, now be very clear that we are going to explain with respect to the first law of thermodynamics, the expression of which is delta E is equal to Q plus W. Now because it is isothermal, so we say that Q is equal to 0, and therefore we come to the final expression, and that is delta E4 will be equal to minus of W4. The result, because it is minus, is simply because that the work is being done by the system. So that's the reason we have delta E4 is equal to minus of W4. So this is, my dear friends, the fourth expression for this particular cycle, and in this way the cycle is also being completed, and we talk about this particular step as adiabatic contraction. I hope you have understood this step very well. Alright, my dear friends, now we move on to the last part as far as the particular expression is being concerned, and here in this case the cycle is complete. The total internal energy will be the summation of the change in the internal energy taking place in all the 4 steps. So therefore I get an expression saying that delta E is equal to delta E1 plus delta E2 plus delta E3 plus delta E4. Okay, this is what I get. Now we had an expression for each and every steps, if you can recollect. So we'll just try to substitute all those expressions into this final expression. So we have delta E is equal to, now when we talk about delta E1, if you recollect, it was Q2 minus of W1. So this is the first step. Now why it was Q2? Because it was the hot reservoir, and because of the sudden cooling, the heat was absorbed, and therefore it was positive. Okay, to maintain the isothermal condition. Next part we go into, and that is plus delta E2. Now when I talk about delta E2, that was adiabatic expansion. In adiabatic expansion there is no transfer of heat, so Q was 0. The work was done by the system, and therefore we say minus of W2. Next is we go into delta E3, that was isothermal contraction. As a result of the isothermal contraction, the gas gets heated up, and therefore to maintain the isothermal conditions, the heat is being liberated. Now when the heat is liberated, I go for minus of Q1, and the work was being done by the system, so we are minus of W3 plus. Now when you talk about delta E4, so that was the last step. Adiabatic contraction, adiabatic, so there is no transfer of heat taking place, and therefore we say the delta E was equal to minus of W4. Once again, the work is done by the system. Alright, so this is, my dear friends, the substitution part. Now what we'll do is we open up the brackets. So we have delta E is equal to Q2 minus of W1 minus of W2 minus of Q1 minus of W3 minus of W4. Okay, this is what we get. So that is equal to, what I do is I take the Q terms together and I take the work terms together. So I have Q2 minus of Q1, that is this and this. Okay, now what I do is I put a plus sign over here, and I get over here is, a minus sign. I'll take common for all the work terms. So we have W1 plus W2 plus W3 plus W4. This is what I get. I keep the minus sign constant. So that is equal to Q2 minus of Q1 minus of Wm. Now what is this Wm is, my dear friends? Now Wm is the maximum work done. Now why do I say it's maximum work done? Because everywhere, if you can talk about, we are talking about the reversible part. Okay, and in a reversible process, you know very well, maximum work is obtained. So maximum work obtained will be equal to the summation of all the work which is being associated with all the 4 different steps. So W1 plus W2 plus W3 plus W4 gives you what? Wm, which stands for maximum work done. So we have this expression saying that delta E is equal to Q2 minus Q1 minus of Wm. Now because here you can see that the process is cyclic. I referred to this word before as well. Now cyclic process is from wherever we start, the initial state, the system comes back after the series of changes back to the initial state. So we started with A, we go through 4 steps, and finally we come back to A. So it's a cyclic process. And because the process is cyclic, therefore we say that delta E is equal to 0. So substituting this, we have 0 is equal to Q2 minus of Q1 minus of Wm. So therefore we have Wm is equal to Q2 minus of Q1. This is the expression that we get. Now, in this case now, if you can just have a look at this very well, the maximum work obtained is equal to Q2 minus of Q1. Now Q2 is the heat which is associated with the hot reservoir, minus of Q1, that is the heat which is being transferred to the sink. So now from this part it is being very clear that the portion of the heat from the hot reservoir is converted into work. Okay, this is what the conclusion I can draw. It's not the entire amount of heat from the hot reservoir being converted into the maximum work. Yes, if the expression I would have got is Wm is equal to Q2, then I would have said that the entire amount of heat from the hot reservoir is completely being converted into work. But here it is Q2 minus of Q1. Okay, so whatever the amount of heat I have from the hot reservoir, I have to subtract it by the heat which is going to be transferred to the sink. So as a result of which, what we have is the Q2 minus Q1. So the amount of heat decreases as compared to the total amount of the heat which is available from the hot reservoir, and therefore I use the word only the portion of the heat. It's not the total heat, only the portion of the heat from the hot reservoir is being converted into work. Okay, so this is something, a very important conclusion that can be drawn from the Carnot cycle. And my dear friends, I am very confident that you have understood the entire Carnot cycle very well. Thank you very much.